This is Garis MPC, Math, Physics, Computing, 130 plus courses at Masters and PhD level in pure mathematics and mathematical physics. This is course number 4, so MPC 4 on linear algebra, a junior senior level course. This is lecture 1, session Z, so our 26th session. We've been through the alphabet. Okay, so we are in section 2 on the solved problems, and we are now still working on complex numbers. And question 123. And here you're asked to prove that the modulus, in other words the absolute value of, so the mod of the sum is less or equal to the sum of the mods. So in other words, mod of z plus w is less or equal to mod z plus mod w. Mod is just short for modulus. It means the absolute value of. A quick reminder, what is the mod of a complex number z? It's sort of its length in a sense, in the Argand diagram sense. It's from Pythagoras, this theorem. So it's the square root of x squared plus y squared. Alright, so as before in the earlier session, let z just be some random complex number, so of the form a plus bi. Similarly for w, another complex number of the form c plus di. Where these A, B, C, D, they're all real numbers here. Okay. Now, take two vectors whose components in two-dimensional real space, and let the components of this vector u, so a little wiggle here, it shows that u is a vector, be a and b, there's reals. And similarly for vector v, its two components are c and d. Why are we doing this? It's convenient. Well, the usual comment, it works. Right, so we're creating a vector using these two components, and we're calling that vector u. We're taking these two numbers and they become the components of vector v. And these two vectors are vectors in R2, so two-dimensional real space where the components of the vectors are real numbers. Alright, so now mod of z, by definition, is the square root of the real squared plus the square of the complex part. So the mod of this will be the square root of a squared plus b squared here. But in terms of a vector, given that these are the components, then from Pythagoras' theorem, because we're in two dimensions, the size, in other words the norm of this is square root of a squared plus b squared, which is this. So in other words, the mod of z is equal to the norm of u. And again, you may say, where are we going with this? But at least you can follow it so far. Now, a similar logic, the mod of w, by definition, here. So it'll be the square root of c squared plus d squared, as here. But given the definition of what vector v was, its norm is also this. So therefore, mod of w is equal to the norm of v. So this equals that. So we're sort of, maybe it's not so obvious where this is going, but we're just setting up the tools that we can use later, effectively. All right. Now, we're trying to prove this. So let's work on the left-hand side. So start with this. So this is the mod of the sum, the mod of z plus w, which is the mod of this. You take them from here. You just add you add the reals, so you get a plus c, and you add the complexes, so you get b plus d times I. You get that. All right. Now, the definition of the mod of a complex number, that's the real part, that's the complex part. Now, the mod of it is, remember, it's the square root of the real part squared plus the square of the complex part. So it'll be a plus b squared plus b plus d squared, the square root of the whole thing. But this is now here you've got another vector. If you, we call it, didn't give it a label, but this, you forget about the norm symbol, the double bars. Just look at this. This is the a vector whose real part's a plus c, and the complex part is sorry. This is just a real vector where the first component is a plus c and the second component is b plus d, and it's a vector that belongs to this space. It's similar to u and v. You could call it w if you like, or I don't know, anything. Now, this is u plus v norm. Where's that come from? What is u plus v? U plus v. So if you add, now you're just adding these two vectors. Remember, to add two vectors, just add the components, the corresponding components. So u plus v will be, the first component will be a plus c, and the second component will be b plus d. And so I've skipped a few terms, but the norm of that will be, if that were just z, how do you define the norm? It's the length, effectively. So it's the square root of the real part squared plus the square of the complex part squared. So let's see. So that's this, and this, the norm of this will be this. Right. Now let's now we can use Minkowski's inequality. That's from problem 117. Remember, it was fairly difficult, but we can just now use it. Here's a summary of the that inequality. It's saying the norm of the sum is less or equal to the sum of the norms, and we can this equals this. You go backwards. So this equals this. So we can write this left-hand side as just this, and now let's see. This equals that. Where's that come from? This equals this, right? So you're just rewriting this equals this again here. But now we use, for this we can use the Minkowski inequality, which is here. So we can this is less or equal to that. So take this term and put it here. So this is now less or equal to that, and norm of u is from here. Norm of u is just mod z, so put it here. Instead of that, just put mod z. And norm of v is here, so mod w. So instead of that, just put mod w. So now we have the mod of the sum. So the mod of z plus w is less or equal to the sum of the mods. So this is less or equal to that, is what we needed to prove. So we've done it. So end of proof sign. Right. Now questions, solved examples in the topic of vectors in Cn. So in other words, n-dimensional complex vectors, or just complex n vectors. Where a complex vector, that means that the components of the vector are can be complex numbers. Right, so question 124, you're given two complex vectors. So you wiggle. The wiggle here means that you use a vector, similar here for v, and we have three components. So they're three-dimensional vectors, complex vectors, belonging to, in this case, C3, because three components, three dimensions of complex numbers. All right, so let's see how many parts in this question. So 1, 2, 3, 4 parts. All right. So the first is just vector addition. You're adding just two complex vectors. So so you're adding this vector to that vector. You know, remember in vector addition, you just add the corresponding components. So in other words, you'll add this to this. That'll be the first in the sum, the result. When you add these two, that result will go into become the first component of your answer of the sum. And the second component will be 4i plus this, and the third component will be this plus 5. So so add them. So you'll get 8 minus 1. There it is here. Add these two. So you'll get 2 plus I. Here it is here. And then add these two, and you get 6 plus 6i. There it is there. So we found the sum. Now we're doing scalar multiplication. The scalar, just a number, but in this case it's a complex number. K, if you like, is now a complex number. It's not with z, if you like. So z here is 4i, and the vector is u, complex vector. So now how to do scalar multiplication? By z, you just multiply each component by z, in this case 4i. So we'll multiply this by 4i. So you'll get 12i, and 4i times minus 2i, so that's minus 8i squared, so it's plus 8. So 8 plus 12i. Now this times this, so you just 4i all squared, so that's 16i squared, so that's minus 16. Okay? And 4i times this, so you'll get 4i plus 24i squared. So 4i plus 24i squared, that's minus 24. So there it is. Okay. Now, a slightly more complicated version of part 2 here. Your z here now is 1 plus I, and you're asked to multiply that. You're asked to multiply the vector v, complex vector v, that's this one, by I plus 1. So I'm just now writing it out in full, so it's I plus 1 times vector v, here it is here again, so just write down here the same. Okay, now so multiply each of these three components by I plus 1. So if you multiply these two, so the reals, you get 5 minus I, plus I squared, so that's minus 1, so that's 4 here. And now the i's, so you get 5i plus 1i, so that's 6i here, 6i, so that works. Alright, now second term, for the reals you get 1 plus 1 by 2 and minus 3i squared, so that's plus 3. So 2 plus 3, that's 5. Here, 5. Okay. Now the complex parts, so you'll get a 2i and a minus 3i, so it'll be minus I, and there it is there, minus I. Okay, now for the third component, it'll just be 5 plus 5i. Alright, there it is. Now we're doing a linear combination of complex vectors, U and V complex vectors. So a linear combination, so a complex number times the vector plus a complex number times another vector. So let's write it out now in full. So 1 minus 2i, and plug in u here. So u is here, so just write that in here. Plus this complex number, 3 plus I, and plug in v. Here's v, plug it in here. Now we just now we multiply these out. So the reals, that'll be 3 plus 4 minus I squared. So that's minus 4, 3 minus 4, so that'll be minus 1. Okay. Well, look, I'll skip over it. I mean, maybe I could have. So just do it for homework. It's just a bit of dull algebra, complex multiplication, and you'll end up. So you multiply this, you'll get that. You multiply these terms, you'll get that. You just check that it's true, and then and now you have 2 complex vectors. This is the first complex vector. This is the second, and you're adding them. So it's vector addition, and so you just add the corresponding components. In other words, you'll add this to that, you'll add that to that, and you'll add that to that. So you just add the corresponding components. So, I can do a little bit. So add this to this. So you get 14 minus 1, so that's 13. Minus 8i and plus 8i, they cancel. So you just left here 13. And so on and so on. So here's your answer. Do that for homework. Pretty straightforward. All right. Now we're doing dot product of vectors, complex vectors, n-dimensional complex vectors in complex n space. You asked to find the dot product of u and v. So here's u and here's v. Now remember the dot product when your vectors u and v are complex. Remember the definition. Here's your definition. Now, I've got 3 bars here by definition. Remember the definition is you take the sum of the product of the components, but the second component you have to conjugate. So don't forget the bar here. You don't have to have a bar when you're talking about real vectors, right? Because if this were a real vector, conjugating it, you're putting a bar over it, won't change anything. So you can forget the bar. But when these vectors are complex vectors, the definition, that's why 3 bars here. The definition of the dot product is that this second component needs to be conjugated. Okay, so now let's see, u dot v. Sorry, forget about that, it's here. I was wondering why it was a 2 here, not 3, because there's 3 components, and here it has a 2. It's because u here is a complex vector in 2 dimensions, so c2, or c squared in a sense. Okay, so and v as well, also a 2-dimensional complex vector. So hence the 2 here, summing over. So form the product of the corresponding components of the first vector with the second vector, but don't forget to conjugate the second vector. All right, well, let's do it. So for the first component, I is 1, so you have u1, that's this here, times v1, that'll be this, conjugated. So just plug this in and conjugate it. So you've got 4 plus 2i, that's here. And second component, so it'll be this times that conjugated. So 3 plus I times 5 minus 6i conjugated. Okay, so now conjugate this, so the I becomes minus I, so you'll get 4 minus 2i, conjugate that. This will become 5 plus 6i, and there it is. Work it all out. Well, you end up with 9 plus 13i. Do that for homework. Check that it works. It gets tedious, these complex multiplications. All right, next question. How many parts does this have? I think I only did one part. All right. Now, you're given a complex vector, 3 dimensions, here, and you're asked to find the norm of that complex vector. And how do you define the norm? Here's the definition here. The norm, remember, is the square root. The norm of a complex vector is the square root of the dot product of the vector with itself, but the itself is conjugated. So here's the dot product. And yes, if you square the norm, then it's just the dot product, but use a complex form. Well, perhaps I could put a bar, make it a bit clear. I could put a bar over here. It just depends how you. So here's the essential. This part here, here. So the norm squared is the sum over the components of the product of the ith component of your complex vector times the conjugate of the component of the ith component. So the sum of ui conjugate. That's the definition. Your 3 bars. The definition of the square of the norm. Okay, from earlier theory. Now, why am I saying this? So, if you now you use just a complex. We're talking about a complex vector, right? So this ui is just a component of the complex vector. It's just a complex number. Right? Just call it z. So when you multiply z by z conjugate, as here. So in this general form, z times z conjugate, where z is just an arbitrary complex number of the form a plus bi. So z times z conjugate from earlier theory, remember, was just simply a squared plus b squared. That's because the complex parts, the I components, they drop out, they cancel each other, and you're just left with reals. So z times z conjugate is a real number here. So it's just that squared plus that squared, a squared plus b squared. We've done that several times. All right, so what? Well, this here is of the form z bar, because it's just a complex number. You could call it. You could rewrite ui as z. So this would be z conjugate, right? So this term here is going to be of the form a squared plus b squared. Right? That's the essential. All right. So let u1 as a complex number be a1 plus b1I, and let the second component of vector u, let that be a2 plus b2I, and so on. And so this will be of the form, so for the first component, I will be 1, so it'll be a1 squared plus b1 squared, right, here. And now you're summing over all. And so for the second component, so say u2 is a2 plus b2I, so this term for I is 2 will be of the form a2 squared plus b2 squared. Similarly for the third term, a3 squared plus b3 squared. So now just calculate. So what is a1 squared? Where's u? Here. So that's your a1 and that's your b1. So a1 squared, so that will be 9 plus b squared, so 16, and similarly here, so this is your a2 and b2, so a2 squared is 5 squared, 25, b2 squared, that's minus 2 squared, so it's 4, a squared, that's 1, plus b3 squared, so it's minus 3 squared, that's 9. So you'll get 25 plus 29 plus 10, which is 64. And now, what are we trying to find? We're trying to find the norm of u. So here we've got the norm of u squared is 64, and therefore, if you take square root of both sides, the norm of u will just be 8, right? Square root of it, 8. So there it is. So we've calculated the norm of u is just 8. All right. Question 127. What are we doing now? How many parts? 1. Just 1? Or oh, I see. I just ran out of rectangles. There's another part. Let me just check. Below, so 2, 3. Yeah. So this question has 3 parts, but I only have space in this rectangle for the first part. So prove part 1, and we'll do the other 2 parts in the next session. Okay, so we'll do the first part, and you're asked to prove. So prove 1, the first one, and that is that the dot product of 2. You got 2 complex vectors here, eh? They belong to they're n tuples, so 2 complex vectors of n dimensions, u and v, and you're asked to prove that the dot product of u and v, so u dot v, is equal to the conjugate of the dot product reversed. Notice that? U dot v equals conjugate of v dot u. So I asked to prove that result. Okay, so let's see. Now to prove the left-hand side equals the right-hand side, you can do that in 2 ways. You can start with the left-hand side and prove the right-hand side, or you can start with the right-hand side and prove the left-hand side. I mean, it's just the same. So you can go left to it, you can go right. Now in the text, Lipschutz starts with the right-hand side. So we'll start, why? Well, I don't know, maybe found it easier. So let's start with the right-hand side. And so here we are with the right-hand side. Now what? So we're conjugating this dot product of v dot u. So here's the conjugate, and now what is v dot u by definition is what? It's just the sum of the product of the corresponding components, and you sum over all the components. Now let's see. So u and v are complex vectors in Cn. So they are n-dimensional complex vectors. So we'll be summing over n components here, and it's v dot u. Now these are complex vectors, so the dot product will involve the second term being conjugated. Right? So you need to. So the second term here, component ui, will need to be conjugated. So I could almost put 3 bars here. So, right? So don't forget, when you're talking about the dot product of 2 complex vectors, your second term here in the definition needs to be conjugated. So don't forget this bar. It's easily done. I mean, to forget it. All right. So okay, now, so we are conjugating the sum of something. Conjugating the sum. Now, from question 121, conjugating the sum is equal to the sum of the conjugating, of the conjugates. Now it's a general. Now we've got a sum here over n things instead of just 2, but it's sort of equivalent. You could prove that. So we're going to use this idea from question 121. I'll say it again. The conjugate of the sum is equal to the sum of the conjugates. Now, if I had a third term here, I could quickly prove that I'd have the sum of 3 things, or if I had n things under this conjugate, I'd end up with the sum of n things. So you could prove that. You can do that for homework if you like. That's pretty readily. Okay, so the conjugate of the sum equals the sum of the conjugates. So here's the sum of the conjugates. Okay, so I've taken this sum outside here, and you can do that from this proof that we did in question 121. All right. Now what? Now using another part of question 121, which says here that the conjugate of the product equals the product of the conjugates. I hope you remember that from earlier question 121. So the conjugate of the product equals the product of the conjugates. So so here you've got a conjugate of products, and we're going to rewrite that as the product of conjugates. So the product of conjugates. So we're going to conjugate that, so that'll become VI conjugate, and conjugate this. So this will be UI double conjugate, like this. So I'll say it again. This is the conjugate of the product. And that's equal to the product of the conjugates. The product here of the conjugates of these 2 things. And that's from a part of question 121. All right, now we can rewrite this as VI, or conjugate, that just stays the same. But UI double conjugate, and that was also from question 121, if you have a complex number and you conjugate it twice, you just end up with the original number. So Z double conjugate is just Z. Okay, so this UI here, doubly conjugated, it just ends up U. So just U here. So this here becomes this. All right. Now these are just complex numbers. Now. So Z1 times Z2, where those 2 are just complex numbers, is equal to Z2 times Z1. Complex numbers are commutative. You can swap the order. It doesn't change anything. The result's the same. The product is the same. So Z1 times Z2 equals Z2 Z1. So I can swap these 2 around. It won't change anything. Okay, so let's do that. So this term here becomes this term, right? So I've just taken these two and swapped them around. And why did I do that? Well, because this, by definition, right, that's the dot product of complex vectors. So this is u dot v, right? And that's what we had to show. So we started with the right hand side here. Here it is here, and this equals blah 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 this, and that's what it's so. And this here is the left hand side here. So in this proof we're going to the left, starting with the right hand side and proving the left hand side, proving this, which we've just done here, and therefore that's the end of using the end of proof sign. We've finished part 1 of question 127, but we have 2 more parts to do in the next session, so I'll stop here.